this next method is a method that's maybe the method of choice for many problems. It's not the method that will beat every method on all problems, but it's a pretty good method. So linear optimization, nonlinear optimization based branch and bound. And so just as a reminder, and so that the slides are complete, I've written down again the mixed integer nonlinear optimization problem here that we just saw a moment ago. So nonlinear objective, nonlinear constraints with these assumptions that the functions are smooth and convex. We have a constraint qualification and the feasible set is bounded. So the boundedness ensures that our algorithms will be finite as long as we don't go back to previously visited assignments, integer assignments. And then the smoothness and constraint qualification ensures we can actually solve subproblems of this form with our nonlinear optimization solvers. Right, so the goal is the previous method that we looked at, Bender's decomposition and outer approximation, they're multi-tree methods. So they search multiple mixed integer linear optimization trees. And that can quickly become the bottleneck because solving a mixed integer linear optimization problem is hard. And each time you do it, you're starting from scratch. There's no information that you can reuse or very little information that you can reuse. That could actually be an interesting project. So we learned also about branch and bound, but that method suffers from the fact that the individual subproblems on the tree are very expensive to solve. So even though you're only searching a single tree, these problems are very expensive to solve. So what we want to do is we want to avoid resolving the mixed integer linear optimization problems like we do for outer approximation and Bender's decomposition, and instead somehow update our mixed integer linear optimization data. So we want to update the problem and do it in a way that ensures that we're still converging. And the interesting part is that this method that I'm going to introduce here can also be interpreted as a branch and cut approach. And if you're familiar with mixed integer linear optimization, then you know that branch and cut is the method of choice. In fact, I used to have a picture of the size of the largest traveling salesman problem that you could solve in any given year. And so this started sometime in the 1950s when people were solving TSPs. And so here's the size of the TSP that you can solve, and here somewhere along here is time. And if you plot the size of problem that you can solve, then it sort of goes up very gradually. And then there's a huge jump. It's really big, and this is on a log scale. And this is when branch and cut was introduced to mixed integer linear optimization. It made a huge difference, this idea by Padbeck and Rinaldi, that you're mixing two different optimization paradigms, the cutting planes and the branching procedure. And so we're going to look at this method here, and I'll just have a couple of slides to introduce the method a little bit, and then we'll go and look at it in detail. So we're going to start off by looking at our mixed integer nonlinear optimization problem that we're solving here. And the idea is basically to set up an initial linear optimization problem. So we're going to solve a relaxation over this polytope where I've got a single linearization point here. So I linearized all my constraints about this point. And one feature of doing this is that the hyperplanes are only touching or tangent if the point lies on the boundary of the feasible set. Otherwise, these tend to be loose. And then we're going to start searching our mixed integer linear programming branch and bound tree. And so we will go to some integer assignment, somewhere down here maybe. And so when we do that, so we start here, we might find that we get to, I think, this point down here. And at this point, we interrupt our branch and bound tree search, and we solve a nonlinear optimization problem, which gets us back to this point here. And then we can update, we can add new cutting planes and update our branch and our optimization problem, the linear optimization problem. So we're creating new linearizations. I have a slightly different way of looking at this. So you start off with a single cut that you generated about your initial starting point. That's the blue cut here. And you set up your branch and bound tree search, and you go away and mix into the linear optimization solver starts searching the tree. So you take this initial tree, and then as you're searching the tree, sooner or later, you will find an integer feasible point. And so when you do that, in this case, here and this branch, you have an integer feasible point, you go back and you evaluate the objective function at this point, and you create the outer approximation cut, for example, or the Bender's cut. That's up to you. That's a choice. And what you now need to do is you need to update all the nodes in your branch and bound tree by adding this cut to the cut that you already had. So I've indicated that the nodes are updated by putting a green dot into the center. So you add the linearizations to the tree. Now the good news is you will only ever store one copy of your linearizations in the tree. You're not going to store separate copies of your linearizations in the tree. So that just goes into a central memory, which makes it efficient. And then there's one caveat, and that's very important, that you need to continue searching the tree, but the node that where you generated the cut has to be added back onto the tree, so you can't eliminate it. The reason is that even though it was integer feasible, there could be other integer feasible points below this tree that might give you a better nonlinear objective value. So in particular, it could be that at this point here, we're integer feasible again, and we find a much lower value. So that's why you need to add this point back in. And that's an important difference to branch and cut for the linear case. In the linear case, once you find an integer assignment and in a particular point in the tree, you know that it's optimal for the whole subtree. So you don't need to do this. In this case, because we're only having a local approximation of our objective function, so we're only approximating the nonlinear objective by these cuts, we need to make sure that there isn't a better nonlinear point. There's a number of algorithms that implement this. It was first developed at Carnegie Mellon University by Ignacio Grossman and Ignacio Quesada, and they implemented initially in AMPL, and we did an implementation later on. Okay, so this was the cartoon, and at this point, you can go to sleep, because now I'm going to go into the details. So if you're not interested in the details, you don't need to pay any more attention. So here's some useful notation for that we need in order to define this algorithm formally. So I'm going to have a set of points P, x, y, at which we have optimality or feasibility cuts. And I'm just going to be loose about that. At some of these points, we might not have an optimality cut, we only have a feasibility cut. And the cuts that we're using for now are the outer approximation cuts, or the first order Taylor expansion about the point x hat. So that's the set P of points. I'm also going to have a set H, that's the heap of open linear optimization subproblems that are on my tree. And then I have one more little piece of notation, which is R min low, which is the continuous relaxation of a mixed integer nonlinear optimization problem. But you don't need to remember that. You need to remember P for points and H for heap. R min low will only appear once. And then there are two subproblems that I'm going to solve, for which I need a little bit of notation. So the first one is the traditional nonlinear optimization problem with the fixed integers. And again, we had this earlier in an exercise. You can also minimize over y, as long as you also add a constraint that y is equal to y hat. And that could actually be advantageous. It's much easier to implement than substituting the variables in. The second problem that I'm going to look at is a node in my mixed integer linear optimization tree. And this is now parameterized by 3 parameters. So in the nonlinear branch and bound, we parameterize the nodes by the lower and the upper bounds that we had created during the tree search. Here, we also parameterize it by P, which is the set of points for which we have our polyhedral outer approximation of the continuous feasible set. So this linear optimization problem looks a little bit like the master problem that we have for the Bender's decomposition or outer approximation, but there are no integrality constraints here. Instead, we have these lower and upper bounds that indicate where in my tree this problem belongs. So this L and U tells you where inside the tree this problem is being generated. Okay, and this slide is a little bit dense, but I don't know a better way of writing this, so bear with me a little bit. We'll go through this. This is basically the whole algorithm that you need to implement. But don't worry too much about implementing it because other people have done it, and I'll show you in a moment how to do it even easier. So you need an upper bound. You keep track of your best solution. That's U. You have your set of points. Initially, there's no points, and you solve the relaxed mixed integer nonlinear programming problem, and then you add its solution to your set of points. So you start off by generating a set of hyperplanes around the relaxation, for example, of your mixed integer nonlinear optimization problem. And you now start your branch and bound mixed integer linear optimization branch and bound by adding your first linear optimization problem to the heap. So this linear optimization problem takes the P that we had that tells us what linearization it has, and it takes infinite lower and upper bounds, which means we're still not unconstrained. And then there's this double loop. The inner loop is a cut generation loop, and the outer loop loops over extracting and adding problems to the heap. So the outer loop is the management of your branch and bound tree. So in the outer loop, you start by picking a problem of the heap. So we just put one there, we take it back out, and we go through this inner loop, and if we ever pop out of this inner loop, then we potentially branch on variables here. So this is where we do the branching, and we add new problems to our heap here. So we have a new point, we do some branching, we add it to the heap. So the outer loop is the heap management or the management of the branch and bound tree. And in the inner loop, you solve linear optimization problems. So this is where you look at what's happening on a node in your branch and bound tree. So the inner loop is just staying at one node in your branch and bound tree. And if the problem that you solve there is infeasible, then you can prune this node. And you never need to look at it again because we created an outer approximation of our nonlinear feasible set. If that outer approximation is infeasible, which is a relaxation, then the nonlinear problem is also infeasible, and we can just prune that node. So that's cool because then once we prune the node, we pop out of here and we can do other nodes. Typically, that's not the case. If the point is integer feasible, so that's the interesting case, then we're going to solve a nonlinear optimization problem. And we want to do that because we want to now generate outer approximation cuts around the solution of my nonlinear optimization problem or feasibility problem. And really, you don't need to worry about this because the nonlinear optimization solvers tell you which cuts you need to generate. So you generate outer approximation cuts here and add them to your set of points. So in the inner loop, you're updating the set of points. You're adding cuts to your linear optimization problem. And then there's just a little bit of housekeeping that says, did I find a better point? So if I solve this nonlinear optimization subproblem and the point is better, then I want to keep track of it because that's my best point so far. Otherwise, I don't need to do anything. And I keep doing around this repeat loop as long as I can add points or as long as I can add new cuts to my problem. Okay, so I'm going to pause here and ask if there are questions because this slide has about 14 lines too many on it for my taste. So has anybody implemented a branch and cut procedure ever? If you have, then you recognize this. Okay, I saw a couple of people nodding in the audience. Very good. So hopefully there were no mistakes here. Okay, let's just move on. But ask questions. Just raise your hand if you want to. Go on.
These cuts that we add they are global cuts at every node. So that's why we are adding them in all the nodes.
Correct. We're only adding global cuts. I'm not doing anything about local cuts here.
Should we add them with all the open nodes?
Yeah, so that happens because I add them to all the open nodes because I only have a single set of points P. And so this set of points P gets updated, and then anything that's on the heap, when I pop it out of the heap, will have that P in it.
But is it necessary to add them to all the cuts?
Oh, now you're asking is it necessary to add the cuts to all the nodes in the tree? And that's a really clever question because I have my branch and bound tree. I'm moving along. I'm at this node here. Let's make this a red node. I'm looking at this node here, and I'm doing my cut generation here. And I could, in principle, now, at the moment, I'm adding the cuts everywhere. So I make sure they go everywhere. But I could just use them in this subtree that I'm looking at here, for example. So those are algorithmic choices and other ideas that you can pursue afterwards. And the next lecture, I'll talk a little bit about the implementation details of how to make this work. This algorithm doesn't work very well. So there's a lot that you need to do, and that comes in the next lecture. So just a couple of comments. The initial implementation, I believe, was done in GAMS. So that's an algebraic modeling system. And that shows you how cool these things are, right? You can implement this really complex algorithm in this modeling system. And it worked. So Quesada Grossman did that. We did it in an implementation using filter SQP.
Did they have to implement branch and cut tree themselves?
Yes, they kept track of the tree themselves. So yeah, you do it for small problems. It's okay. We did this using filter SQP and Minto. Minto is a mixed integer nonlinear optimization package by Martin Salversberg. This basic framework works okay, but it's not very fast. You need a range of additional features to make this work. And there are versions of it in Bonmin and Minotaur, which are much more recent. And you could, in principle, extend this to global optimization branch and cut approaches and so on. So there's lots of extensions there. So, but hang on a second. At one point, I said, if we add cuts to this problem, we can't just delete it from our branch and bound tree. Why do we need to do this? I just want to emphasize this, because once I add a cut to a node in my tree, the integer assignment that I found there is no longer valid. It's no longer a solution here, but there could be other integer points for the nonlinear problem that I haven't visited yet that I may need to revisit. So just to re-emphasize, that's a very important difference to traditional branch and cut. Okay, so this is arguably the best way of solving mixed integer nonlinear optimization problems. It's not the one that will solve all problems the fastest, but it's probably the one that solves most problems the fastest. And there are various implementations. To make it work, you need additional features, and I'll talk about this on the next set of slides. One thing that's clear is you want to reuse the tools that go into it. So when we implemented this using Minto, we made use of all the tricks that Minto had that made it actually an efficient solver. And the nice thing is, you only have one tree that you need to search. You don't lose the information of the tree search that you've done. The last point is it's maybe a little bit of a stretch to call it branch and cut. And this will become clear in the next lecture, because you will see that you generate these integer solutions, you generate very, very few of them. And so you really want to make it more like a branch and cut algorithm. You probably want to start generating cuts at other points that are not integer feasible as well. And that's what's actually done as well in some of these algorithms. So with that, this is the coolest algorithm for MinLo. But let me know if you have questions, please. Yes. Oh, there was someone. No, he was up first.
So if we add a cut in all the branches at all the nodes, is it possible that we are also cutting some physical region?
No. So the reason is that the outer approximation cuts are outer approximations of the the convex functions. So they're always of the form where I have some nonlinear constraint, and I have variables x and y. So y are my integers. So those would be my feasible sets. And they're always of the form that when I initially solve my linear programming relaxation, if I hit an integer point, I might hit it out here. I will linearize this nonlinear constraint here. And by linearizing this nonlinear constraint, I ensure that I never cut off. I can never cut off points. That's the nice thing about convexity, that you're always creating a supporting hyperplane. And it doesn't matter where in the tree you do this, because the nonlinear constraint is valid throughout the tree. So what you're doing is you have this nonlinear constraint that you worry about, but you're not looking at it while you're searching the tree. You're only looking at linearizations of it. Just occasionally, you want to make sure that you want to tighten and get closer to the feasible set. And the reason why it's not cutting off is because the cut is always a cut in all my integer variables and all my continuous variables. So it's always a global cut. So my outer approximation cuts are they're always global cuts because they involve all variables. So even though I generate them in a point in the tree where some of the variables are fixed, I take that fixing out before I generate the cut. That's the key part. And I think that was your question, because in branch and cut, your sort of fixed points, I already fixed, when I get to this point, I've already fixed two variables. But I take that fixing out and then generate the cut. That's why it is. Sorry, I didn't understand your question correctly, but now I think I have a better answer.